Hi, Physics 30s, Mr. Thompson here. All right, we're looking today at the models of the atom. We're on Unit 5 on atomic theory. All right, we're looking at the billiard ball model in 1810. All matter is composed of atoms. Atoms are the smallest particles, quanta of matter. There exist no subatomic particles. There are some advantages and disadvantages. You can see those, okay? Explain chemical reactions very well. In other words, law of conservation of matter, nature of elements, nature of compounds, and it couldn't explain why molecules form and the repeated properties of elements on the periodic table, why they're grouped into families. All right, cathode rays. Crookes, 1879. In a cathode ray tube, a CRT, two parallel plates are placed within a glass tube and attached to a high voltage source, as shown in the diagram here. When the gas pressure was reduced inside the tube, colored rays were observed moving from the negative plate cathode to the positive plate, the anode. Thus, these rays were called cathode rays. All right, were cathode rays particles or waves of electromagnetic radiation? Scientists showed conclusively that the cathode rays were discrete negative particles and not EMR. Well, cathode rays deflected in magnetic fields and electric fields as a negative charge would. EMR would not deflect in either field. And so you can see here that this one, in the first diagram on the left, we're using the third left-hand rule for force. And so if you put your fingers right into the page and your palm points down for the force, the thumb points to the right for the charged particle's velocity or speed. And then you can see that the force going downward causes it to curve downward. Okay? Magnetic field into the page, that's what I was talking about. If you take a look at the second diagram here with parallel plates, you have a positively charged plate and negatively charged plate underneath. Well, the charges were deflected upwards when they were sent horizontally through those plates. And that would be the same thing as if they were negatively charged. Okay, let's look at Thomson's raisin bun model in 1897. We also call it the plum pudding model. Discrete negative particles inside cathode rays were called electrons by J.J. Thomson. When electrons were emitted by the cathode, there was no change in mass or deterioration of the cathode metal. This was clear evidence that electrons were particles smaller than atoms, which defied Dalton's model. Thus, a new model was needed to account for the existence of electrons inside the atom. Thomson suggested that the electrons were distributed evenly in the positive fluid, much like raisins in a bun. So the electrons were embedded in a positive fluid and distributed evenly. And they had a very small mass. The positive fluid was most of the mass and volume. Uniform density, equal but opposite charge as electrons. Because, of course, the atom is neutral, so same amount of positive charge as negative charge. All right, in Rutherford's scattering experiment, this disproved the idea of this positive fluid from Thomson's model. So Rutherford tested the Thomson model of the atom by firing alpha particles through very thin gold foil. The prediction is that Thomson's model predicted that the gold atoms were of uniform density. As a result, there should be no deflection. The alpha particle should go straight through the foil and have 0-degree deflection. But the actual results, most, right, 99.99% of the alpha particles went through with little deflection, less than 10 degrees. However, 1 in 10,000 were deflected by more than 10 degrees. Very rarely an alpha particle even deflected at 180 degrees, so straight back from where it came. And Thomson's model had no explanation for the significant deflections, like greater than 10 degrees. All right, we're looking at Rutherford's planetary model. Rutherford postulated that most of the atom's mass is contained in a tiny nucleus, and this nucleus is a very large positive charge. To account for the volume of the atom, Rutherford suggested that electrons were in orbit around the nucleus. And so now we have a central nucleus. In fact, Rutherford coined the term nucleus, a small, densely, positively charged location in an atom. So you have empty space, takes up most of the atom, 99.99%, and then, of course, the electrons moving in orbit around it. Okay, nucleus, of course, contains most of the mass of the atom. Rutherford's planetary model well explained the results of the scattering experiment. Most alpha particles went through with no deflection. Why? Well, the gold atoms are mostly empty space. The alpha particles move through with no interaction with the gold atoms. A few scattered at significant angles. So the alpha particles that get close to the nucleus are deflected by electric repulsion, like charges, because a positively charged alpha particle is deflected or repelled by a nucleus, positively charged nucleus. The closer to the nucleus, the greater the deflection. This was verified using Coulomb's law. So, of course, a scattering pattern was observed as shown in this diagram. If the alpha particle traveled head-on, it would reflect straight backward. Major problem with the planetary model: if the electron's in orbit around the nucleus, then it is constantly accelerating centripetally. An acceleration charge should emit EMR, based on Maxwell's theory of electromagnetic radiation. Thus, the electron should constantly be losing energy and would spiral into the nucleus in a very short time, 10 to the negative 8 seconds. So let's look at the properties of the electron, charge and mass. The charge to mass ratio of the electron. Thomson in 1897, he used a modified CRT below to investigate the properties of the electron. So essentially you have a large potential difference. You have a cathode where electrons are emitted. They are accelerated towards the anode. They move through and into a region where there's parallel plates. Okay? So an electric field is created and coils of wire on either end, making essentially a magnetic field. Okay? So Thomson turned on both fields so the cathode rays went through undeflected. So Newton's first law, well, they're balanced forces. The magnetic force and the electric force are equal to each other, and you come up with this equation. The speed of the particles is the magnitude of the electric field over the magnetic field. We call it a velocity selector region. Okay? Using this approach, Thomson was able to determine the speed of the electrons because only electrons of a certain speed would go through undeflected. Okay? Thomson then turned off the electric field, so there was only a magnetic field. The electron would be deflected into uniform circular motion. And so we could equate the magnetic force with the centripetal force.
Piece of the